Okay, welcome back to Real Analysis. We're going to continue our work in Chapter 2 on sequences of real numbers. Section 2.6, we're going to look at a kind of a class of sequences called bounded sequences. Bounded is an adjective that we've already applied to subsets of real numbers, so let's start by reviewing what we mean by that definition. Okay, so if you're giving me some subset of real numbers, I'm calling it E. It's called bounded. I'm not saying bounded above or below, but just bounded. So in particular, when I say something is bounded, I mean it's both bounded below and above. And more precisely, I mean that there exist some numbers, say little m and capital M, such that if you take any value of x in E, that value of x is greater than or equal to little m. That is, little m is a lower bound for E, but it's less than or equal to capital M. Capital M is an upper bound for E. So a subset of the real numbers is bounded if it fits in some interval. If it's a subset, so I can kind of write down here parenthetically, not quantifying the variables again, E is completely contained in the closed interval between little m and big M. Okay, so it's bounded in that sense, that it's inside of some interval. Little m being the left endpoint is the lower bound, a lower bound for E, excuse me. It's not necessarily the greatest lower bound or anything like that. It's just a lower bound. Likewise, capital M is some upper bound. So E fits inside of some interval. Intuitively, a bounded subset means that there are no elements, that elements of this subset are not kind of arbitrarily large or arbitrarily small in the sense of negative numbers being small. I'm going to leave it as an exercise to you. It's mainly just kind of a notational convenience, but you can always, if you like, for a bounded set, assume that the interval that contains that set is symmetric. So you can always take a lower bound to be the opposite of an upper bound if you have and not any lower bound, but there is some upper bound of a bounded set so that its opposite is a lower bound. I'm going to leave that as an exercise to you, that E is bounded if and only if you can actually find some number M that every value of X in E is between minus M and M. All right, so this interval that contains your bounded set, if you like, can always be taken as a symmetric interval. Symmetric in the sense that it's centered symmetrically around the number 0 on the number line. So that's a little informal exercise for you. Maybe you can stop the video and do it right now. Maybe you can stop the video and do it right now. You kind of might want to think, and there's lots of ways to approach it, but you could kind of think in terms of cases about whether m was positive, a little m was positive or negative, and so on. But yeah, good. Okay. So what's the relationship between bounded subsets of the real numbers and bounded sequences? Well, let's just start by remembering that a sequence is a function, right? A sequence of real numbers is a function from the natural numbers into the real numbers. Functions have a range. The notation for that, or an image rather, the notation for it is like that, S of n. So it's the range or the image of S. It's those real numbers that are equal to S of something, right? And the range of this function is a subset of the real numbers. Okay, so that's kind of the motivation for our main definition here. I'm going to say that a sequence is bounded if its range is a bounded subset of the real numbers. All right, so if we take that exercise that you've done and said, well, a bounded subset of real numbers lies in an interval between minus m and m, then we can kind of re-quantify this definition and say that a sequence is bounded if there's some number m. So there's an existential quantifier here, very important to keep track of that. If there's some number m such that all sequence terms in absolute value are less than or equal to m. So again, by our definition, that just means, or by properties of absolute value rather, that the sequence terms are between this minus m and m. Yeah, or if you like, that the range of the sequence, the range of the function, is in the interval from minus m to m. These are all just sort of different notational ways of writing down the same thing. Let's look at some examples. Stop the video and soak that definition in. I'm just going to charge forward as usual. So let's take a sequence whose terms are, say, n over n plus 1. I claim that that's a bounded sequence. Well, because n over n plus 1 is a positive number, so it's greater than or equal to -1 in particular. But for every natural number, n over n plus 1 is less than or equal to 1. Yeah. So it's a bounded sequence. Its terms lie between -1 and 1. In fact, they lie between 0 and 1. But I'm just using a symmetric interval. How about another sequence we've looked at before? This alternating sequence. Its terms are 1 and -1. Yeah, so if n is even, that term is a 1. If n is odd, it's a -1. So in particular, every one of those sequence terms lies between -1 and 1. It's a bounded sequence. Nice. We proved in the last lecture that the square root of n diverges to infinity as n goes to infinity. Well, in particular, among other things, you conclude that therefore that this sequence is not bounded. It's not bounded because what does this mean? This exactly means it's actually if and only if, no matter what m you try to pick, right? There exists some number, capital N, some natural number, such that when the index little n exceeds that, the square root of n is bigger than or equal to your capital M. In fact, you can even arrange it to be strictly bigger than if you like. All right. So that means that the range of this sequence does not stay in any bounded interval. It doesn't stay in any interval between -m and m. Nice. I'm sticking to these kind of algebraic functions. Maybe we could just kind of make up another one here. You could similarly show that, say, something like 2 to the n is not bounded. It's not a bounded sequence. That the powers of 2 grow without bound. But in order to kind of rigorously prove that, in fact, 2 to the n goes to infinity, then I would need some kind of properties of the exponential function that it's not like you don't know them. In particular, that there's a logarithm base 2 and that logarithm grows without bound and such and so on. But we just haven't kind of developed that yet. So that's why my examples in this course are kind of sticking to elementary algebraic functions, polynomial functions, the square root function. But you can certainly expand on your own. Think about other sequences that you've seen in the calculus course. And then, I mean, anytime you're using sort of their properties, some of those properties we haven't developed here. And that's why they kind of don't show up in my lecture notes. Cool. All right, so there's some examples of sequences that are bounded, sequences that aren't bounded. The main theorem, the only theorem here in this section, and this is kind of intuitively obvious, I think. If you take a convergent sequence, a sequence that approaches a limit, well, then it has to be bounded. If the terms of your sequence are going to get arbitrarily close to some number L, then the terms in your sequence cannot, be arbitrarily big. But that's just intuition and kind of hand waviness. Let's see if we can't give sort of a rigorous proof here. So what am I going to be assuming in my proof? I'm going to assume that I've got a convergent sequence, any convergent sequence, and then I'm going to try to show that it meets that definition of boundedness. I'm going to try to find the interval in which all of its terms live. So here we go. Let's see if we can't do it. Let's take some convergent sequence, call it Sn. My proof is starting with an arbitrary convergent sequence because I'm trying to prove a statement about all sequences. And now I'm just going to unwind a definition. If it's a convergent sequence, it has a limit. So there has to exist some real number L. Yeah, it's not infinity because infinity is not a real number. There has to be some real number L such that my sequence converges to L. That's just the definition of convergence. Now I'm going to use that limit definition. For every epsilon, these terms are supposed to become within epsilon of that limit. So in particular, if I say take epsilon equal to 1, okay, it's kind of an arbitrary choice. You could take any positive number that you like, but if just for convenience, I'm going to take 1. I have to be able to find some natural number, capital N. Here I'm emphasizing that it depends on my choice of epsilon, so that the distance between my sequence terms and my limit is less than 1 when n exceeds that natural number. Okay, but now I'm going to use the triangle inequality. the absolute value of my sequence terms, I'm going to add and subtract, or subtract and add rather, the limit from my sequence terms, and then use the triangle inequality. That sum, if you want me to kind of parenthesize how I'm looking at it, I'm looking at Sn minus L and L as the two things I'm adding together. The triangle inequality says that sum never exceeds the sum of the absolute values. The absolute value of that sum never exceeds the absolute values of the terms, right? But if n is greater than or equal to n, we said that Sn minus L is less than 1. So I'm just replacing Sn minus L with a 1, making the result bigger because my n exceeds capital N, right? Okay, so what does that mean? That means that the tail end of this sequence is kind of bounded, right? My sequence terms are never any more than 1 plus L, well, as long as n is at least capital N. But before that, there are capital N minus 1 terms before that, S1, S2, and so on, those sequence terms might have been bigger than 1 plus L. I don't know. But there's only finitely many terms before that. So here's what we can do. I'll just take my M to be the maximum. I'm writing a finite set here, so the maximum is one of its elements. I'll just look, how big is the first term in absolute value? How big is the second term in absolute value? Go all the way up to S capital N minus 1. So throw all of those in there, and then also throw in this number, 1 plus absolute value of L. All right? So it's certainly the case that the sequence terms never exceed that because, well, we've constructed capital M that the first n minus 1 terms are no bigger than it, right? They're no bigger than the maximum of that set. And then after that, the infinitely many remaining terms all have little n bigger than n. And we've already said that all of those are less than 1 plus L. So by throwing 1 plus L in there, we've gotten that tail end of the sequence to be less than or equal to M in absolute value as well. All right. So by definition, I've found a bound, capital M, on my sequence. That is, the sequence is bounded. Cool. You should maybe try to draw a little picture. See if you can draw a little picture to kind of explain to yourself what this proof is saying. That by conditioning with epsilon equal to 1, I found a place that if I go out past it, I'll stay within 1 unit from L. And then I just kind of threw in all the possible sequence terms that would happen before that. And as long as I take a number that's greater than or equal to all of those finitely many numbers, then I got my bound. Nice. All right, I'm going to try to keep this one short. There's a corollary. I'm kind of questioning whether I should call this a corollary because it's really just the same statement by contrapositive, but it's an important contrapositive. So maybe if you'll allow me to kind of write just in chalkboard talk here, kind of as a summary, let me make a couple of vertical lines here. What we just proved, if I were writing it in kind of blackboard notation, I just proved that if a sequence is convergent, then it's bounded. Okay, so the contrapositive of such a statement, remember the contrapositive is that you negate both statements in the implication and reverse the implication. So the contrapositive says that if a sequence isn't bounded, then it's not convergent. And that's all my corollary is. So it's really sort of not a corollary. It's just the contrapositive of the statement that we just proved. It's equivalent to it. But it's important. If a sequence is not bounded, then it cannot converge. And if it cannot converge, then it diverges. All right. Okay, so that's it for this short lecture. Thanks for listening.